Hi everyone. My name is Bruno Pannunzio. I'm a postdoc at the Advanced Bioimaging Unit at the Institut Pasteur of Montevideo. And I've been part of the team developing PhasorPy, which is the Python library I will be presenting today for phasor analysis. I will share in the chat a link to there you go, to a Google Colab notebook for everyone that wants to join and run the code as we go through it. You can do it. You have to create a copy to your drive to be able to edit, so feel free. Also, there is a Q&A section. I will be reviewing it every few minutes, so feel free to ask any question there. So let me share now this screen. Okay. So this is the Jupyter notebook that I shared with you. This we will go through some examples of synthetic and real life examples for fluorescence lifetime imaging and hyperspectral images. And the idea is that we go through the main functions that this FhasorPy library has up to date and see different approaches of how to use them. So first of all, I will also share with you this the link for the let me share. Where is the chat? I don't know where the chat is now, but you can go to the web for FhasorPy, is phasorpy.org, where you can see all the documentations, and we will go back and forth between the Jupyter notebook and the documentation to see what each of these functions we will be using from the signature and its applications. So first of all, let me know if you have any issue with opening this Jupyter notebook in your own system, and we can see what can we do. So as I said at the beginning, the idea of this workshop is to go through some examples of FLIM, fluorescent lifetime imaging, and hyperspectral images using the PhasorPy library. So the idea is not to go much in depth into the phasor analysis because we are a little bit time constrained, but go directly to the functions of this library and how to use them. But if you have any questions, again, you can ask them and we can go through them. So the first step will be to install the PhasorPy library in your own virtual environment. The advantage of using these Google Colab notebooks is that everything is pretty much ready to use. So the only thing we need to install is the PhasorPy library, that we can do it via pip, so simply with pip install. And it will install all the necessary packages pretty fast. And we will also need to import another very commonly used packages as matplotlib and numpy, as well as tfile, that we will be going to be using throughout this tutorial. So the first thing we're going to go through is some of to understand how these fluorescent lifetime images are formed. We're going to synthesize some signals and then transform them to the phasor space using PhasorPy. So as you see in the description of each code cell, we have the different functions that PhasorPy has, and you can go directly to the link that is linked to that function And this will take you to the official FhasorPy documentation, where you can see in very much detail all the signature of the function and everything related to the parameters, returns, and examples, and much information about this each of those functions. So feel free to click on each of these links to get more information about them. So the first one we're going to use from the FhasorPy library is the lifetime to signal function that is in the main module of FhasorPy, which is the phasor module. At the moment, that you can see here in the documentation that this module has very diverse set of functions to calculate, convert, calibrate, and reduce the phasor coordinates. So these are all the functions that are already there in the library, ready to use. And we are going to go through some of them, of course, because we don't have much time. But everything is there to be used. So first, we're going to go through this module, phasor module, and particularly with this lifetime to signal function that, as you can see, if we go to that link, this is a function to return a synthetic signal from lifetime components. So here we are going to run this code, which simply here we synthesize the signal using the frequency, which is 80 megahertz, and the lifetimes of 4 different components. We're going to see 4 different, I don't know what happened there, 4 different components with different lifetimes and the different decays. So here we go. We use the matplotlib library to plot these decays, and as you see, the signals created with shorter lifetimes are shorter in time. Longer lifetimes, as the red one, is more has a longer decay. So this is simply just to generate some synthetic signals, and now we are going to transform that signal to the phasor space. So to do that, we're going to use the phasor from signal function, which is also in the phasor module of FhasorPy, which this is a very important function of this library, a main function. And this function accepts a signal, any signal for frequency domain, time domain, or hyperspectral data. And it returns the phasor coordinates, the mean or the average signal along the axis, the real component, and the imaginary component of that signal transformed into the phasor space. So this function is optimized with Cython, so it works very fast compared to other algorithms, for example, the NumPy FFT. And because also this function only computes the phasor of this specified harmonic. So we can compute by assigning the harmonic parameter to all. We can compute all the harmonics possible for that signal. But if we know we're going to use only some of them, we can specify it. By default, is the first harmonic only computed, and this reduces the execution time for a 4-fold approximately compared to the NumPy FFT, depending on the number of harmonics computed. So this phasor from signal function can be used for either the time domain, the frequency domain, or the hyperspectral signals at the same using the same function. This will compute the G and S, which are the real and imaginary components of the normalized Fourier transform, and then we can use these phasor coordinates to perform all visualize and perform all the phasor analysis. Here we are going to transform this previous signal, synthetic signal that we created, And we are going to use this by running this phasor from signal and just running the signal to that function. So then we are going also to calibrate this signal using a reference of known lifetime. I'm not going to go much into detail now with this because we will see more of this when we analyze as a real example image. So to run this, we just we're going to transform this signal and then calibrate it, and then we just plot it using this phasor plot, which is phasor plot class, which is present in the phasor plot in the plot module of FhasorPy. So maybe we can go now to that plot module, where you can see that here we have this main class, which is phasor plot, which we can use it to plot these phasor coordinates, and we will go through different examples. But this will be used for FLIM and also for hyperspectral images at the same time. And so let me go back to the notebook here. So once we transform the signal, we calibrate with a reference known lifetime here, and then we plot this, and we see that each of the 4 different decays are located in the semicircle as expected since they are single exponential signals. So now we can synthesize a multi-exponential decay also with the phasor from lifetime function. And here we assign some fractions for each of these 4 components. So we have a mixture of exponentials. And this we do it here in the phasor multi-exponential, where we just give the fractions to this function, as well as the frequency as the lifetimes as before. So now if we plot this, we will use also the phasor plot class to plot this new multi-exponential decay. And we should see that now this component, this phasor point is located inside the universal circle, since it's not a pure component, it's not single exponential, but the mixture of these 4 components. So now we can go through, if you don't have any questions. I see that there are no questions. We can go through a real example. We are going to start with a FLIM image, which is we are going to use an image from the FLUT library, which has in Zenodo here the embryo file with its an embryo image of TCSP, and it's corresponding here the fluorescence used for calibration. So we are going to use these 2 images, which can be retrieved using the fetch function from the dataset module of FhasorPy. So we can go through this dataset module. And here you can see that we have some available datasets that can be retrieved using this fetch function. As I said, we're going to use the FLUT dataset for this example. So to read this file, since it's a T file, we're going to use the T file library, but FhasorPy has an I/O module that contains a lot of functions to read different formats of FLIM and spectral imaging. You can see here that these are the supported file types of the library at the moment. We are planning to support other file formats, but the main file types are here. As you can see, the LSM for the hyperspectral images. Then you have the ISS, Becker and Hickel, the SDT, PicoQuant, FLIMBox FBD, FLIP, and also some SIMFCS file formats. So as I said, this embryo file is in TIFF format. We're going to use the TIFF file library, But so you know, we can read many other file formats using FhasorPy. In fact, when we go with the hyperspectral example, we are going to use one of these functions. So first we fetch this file, and then we read it. We read and create the signal. So as you see, we have a 512 image and 56 time beams. So, and these time beams are located in the first axis. So this is important because we now need to specify this to the function we used before. I will go into that when in a couple of moments. So it's always good to check first that the signal makes sense, and for this we are going to use the plot signal image from the plot module. And this we just give the signal, and we have to specify the axis if it's necessary. And then we can see here that, as I said, the time beams are in the first axis, so we need to specify in this case, because by default it gets the last axis. So here you see that we, with this plot signal image function, we can see the average image, the mean image generated after the transformation, and here we can see also the mean decay of all the images. So this is just to check that the signal makes sense, and we can go on with the phasor analysis. So to transform this signal, we are going to use this the same function that we used before, the phasor from signal function. And in this case, we have to also specify that the time beams are in the first axis. Here we can use also this plot phasor image function, also from FhasorPy, from the plot module to plot the GNS coordinates also as an image if it's necessary. So we can go through this again with this now. So as I said here, we give the signal now that it was read using T file, as you remember. And now we specify the first axis, and here we say that, which is also the default, we are going to compute only the first harmonic. But if I can show you later what happens if we can compute also all harmonics or the specified harmonics simultaneously, and also very fast. So here we plot the mean, which is the same as before, and then we have the GNS from the first harmonic as images also using this plot phasor image function. So as you can see here, we can change the number of harmonic to be computed. Like here we're going to calculate the second harmonic, and we'll see a slight change in the GNS images. We see here some changes. Also, we can see a lot less detail, of course, because we're going into higher harmonics. And if we want to compute specific harmonic, we can give this as a list. For example, if we want to compute the first 3 harmonics, we specify which ones we want, and this also retrieves the real and imaginary components of these 3 harmonics. So the 3 harmonics are will be stored in these real and imaginary arrays, all in the same array. So here we see the first, the second, and the third harmonic of the GNS images. So I will go back to the first harmonic only for simplicity, and then we can plot now these phasor coordinates generated from this embryo image from the first harmonic. And we're going to use the same class as before, the phasor plot class from the plot module. And in this case, we're going to use a 2D histogram generated from these phasor coordinates. But this phasor plot class also accepts contour. We can also plot as contours or as a scatter plot if needed. So we can go now to plot this as a his2D inside this phasor plot class. Is a method for this class where we can specify the color map and the time bins just the same as when we use matplotlib. It's kind of a wrapper for matplotlib, this phasor plot class. So here you see these are the raw phasor coordinates, uncalibrated and unfiltered. So we see a lot of spread and it's this cluster is outside of the semicircle. So we see this needs to be corrected. So we can change the color map if we want. Here we can use any of the matplotlib color maps that are specified from here, and you can go through any of them if you want. And then, for example, here we can change this color map and also the number of bins if we want more or less bins for the 2D histogram. So once we plot and we realize the need for calibration, so one of the advantages of the phasor approach is that we don't need to model the IRF. But if we know we have a reference file with no lifetime or a zero component, we can use this to calibrate the other image, which is fast, and we don't need all the other modeling, for example, for the heating analysis. So the calibration, what it does is performs a phase shift and also a modulation correction. So calibration is done in the polar space, and then this is translated to the phasor space. So in any case, all we need to do is call now this phasor calibrate function from the phasor module. And here, as you can see, it receives as input the real and imaginary that we want to be calibrated, and then the reference real and imaginary components of the known lifetime. Then we also need to specify the frequency and the lifetime of that reference. We can perform some other things, but I'm not going to go into detail now. But here we will get first the reference file, also fetch from the FLUT dataset, and we are going to convert to transform this reference signal to the phasor space. And then here we are going to calibrate the real and imaginary, which we plotted here, that are uncalibrated and unfiltered, using the specified frequency, which is 80 megahertz, and the known lifetime of the fluorescence, which is 4.2 nanoseconds. So then we're going to use the same phasor plot function class to visualize this calibrated phasor coordinates. So we should see now that the cluster of phasor points should be inside the universal semicircle. And indeed, we see that it's here. All this spread we are going to remove it now, but the main cluster, we see that it's now calibrated inside the universal semicircle. So as I said, this is performing the polar space, but it always works with as inputs with the phasor coordinates. So there is no need to go back and forth to the polar space. So another common method used for phasor analysis is the filtering and threshold to remove all this spread and remove also the pixels with low intensity. So first, we are going to apply a median filter to the phasor calibrated phasor coordinates. And And for that, we're going to use the phasor filter function, which is from the phasor module also. As you see, the phasor module is the main module with all the phasor transform functions. And at the moment, this function only has one method, which is the median method, where we are planning to expand this to other method of filtering. For example, the wavelet filter will also be included in the short term. So this phasor filter function receives the real and imaginary phasor, the components. And then we can also specify the number of times we apply this filter. This is because applying this filter more than once is also used to improve the contrast and reduce the noise. So in this case, by default, we will use a 3x3 kernel size, but also a commonly used kernel size is 5x5 if we need more filtering. So then we will also use, I will apply the filter and threshold later at the same time. So now I will go through the thresholding, which is also a common thing done with phasor analysis, which what we will do is remove all those pixels that in the mean intensity image are below a certain threshold. So this will remove a lot of noise. And for that, we need first to recognize which is what the threshold value we're going to use. And for that, we can simply plot a histogram of the mean intensity image to visually check which value we can use. We can also use some automatic threshold function for like the Otsu threshold, but in this case, we are using a manual threshold. And here we use the threshold of mean intensity 1. So all these pixels with mean intensity value below 1 will be removed from the phasor coordinates. So for the thresholding, we are going to use the phasor threshold function, which is also in the phasor module. I will go through it fast. So this function also accepts the mean, the real and imaginary components of the phasor. And here we can specify a wide variety of thresholds. So we can specify a lower and upper threshold for the mean intensity image, which is these two parameters. But also we can specify thresholds for the real and imaginary components, as well as a threshold for the lower and upper phase angle and modulation. So this function is quite can be used for thresholding in many different aspects, and this will be translated to the mean, to the real and the imaginary components of the image. So for example, if we threshold based on the real, we will also remove the pixels that are below the threshold in the imaginary and in the mean intensity image. So that's what I meant with it's translated. So we can use this here, and as I said, we are going to first filter the real and imaginary components separately. So the filter is applied to the G and S separately. And here, as I said, we specify a 3x3 kernel, and we will apply this filter 2 times. We can apply as many times as we want. In this case, we're going to use it only 2 times. So then we are going to threshold the pixels that are below 1 in the mean intensity image. So here is where we specify this. And then we are going to plot using the same class as before, the phasor plot with the 2D histogram. This filter filtered, thresholded, and calibrated phasor coordinates. There we go. So we see now that all this spread is removed. So we see a much clearer, much contrast in the phasor plot, thanks to all this pre-processing done to these coordinates, to these phasors. So until now, we did only some visualization and some processing of this phasor data, but now we can also take advantage of this reciprocity principle from the phasor analysis, which is that we can go from the phasor plot to the image and vice versa. So there is another module from PhasorPy, which is the cursors module, which has some functions to mask some regions of interest in the phasor plot with different shapes, and also to create some pseudo color imaging. So we'll go through them here, and the first we are going to use is the mask from circular cursor, which we will create some circular cursors in the phasor plot, and then we will use those masks generated to create a pseudo color image. So here we specify the center of the circles of the cursors. So we are going to use two cursors in this case. So one is located at the 0.69 in the G. So it will be here, the first cursor, and the second cursor will be here. So we specify the center in the real or the G and S coordinates, and the radius for each cursor. So we can also specify different radius for both cursors if we want. As a list, in this case, I will just use the same for both. So here I am just going to plot these two cursors in the phasor plot to see which are the regions of interest. And then here with mask from circular cursors, we are going to get these masks generated from these cursors. Then I will run this, and then using the pseudo color function also from the plot, cursors module. Here we can go to see what it does. Here it receives the masks generated by the cursors, and we can also overlay, blend the mean intensity image with these masks and with colors to generate the pseudo color image. So comes an error here. Well, maybe it's here. We can then here, as I said, here we generate this pseudo color image. And we overlay or blend the mean intensity image with the masks, and then we just plot this. So here we selected these two cursors, the red and the blue circles, these regions of interest, and we create a mask to see which pixels correspond to these regions of interest in the phasor plot. So we see here that these red cursors are all these red pixels, and the blue cursor are these blue pixels. So this is overlaid or blended with the mean intensity image. But as I will show you later, we can also just use the pseudo color function to show the masks without blending with the mean intensity image. So another thing we can do with PhasorPy is perform some component analysis, and we can use different functions located in the components module. So this module we didn't go through yet. So this module at the moment contains two functions to perform 2 and 3 component analysis, but in the very short term, we are going to add the functions for n component analysis and the blind component analysis also. And we are first going to use these two functions from Phasor to get the fractions for each pixel of the two components. So here we go to this function, and we see that this function receives the real and imaginary components and the real and imaginary components of coordinates of the pure components. So here we are going to specify the lifetime of the two components, which are the 0.5 nanoseconds and 4 nanoseconds. Then we are going to get the phasor coordinates of these components with phasor from lifetime, which receives a lifetime and returns the phasor coordinates in the universal circle. Or if we have the fractions, we can also get the phasor coordinate from a mixture of components. So now, then we are going to use these two fractions from phasor function. As I said, we give as input the real and imaginary components of after all the processing of filtering and thresholding, and then the components we generated from this lifetime. So then we plot, and just to see where are the components, and then we are going to plot with Matplotlib the images generated from this fraction, and for each fraction, the fraction of each of the two components in the image. So here we see these are the two components of the lifetimes we specified, which is 0.5 nanoseconds and 4 nanoseconds. So we are going to get the fractions for all these phasor points for these two components. So this actually these two fractions from phasor component returns the fractions only of the first component, but is to get the fractions of the second component, we just have to subtract 1 minus these fractions of the first component because they are complementary, which is what we are doing here. So then we plot these fractions, and we get for each pixel which fraction of the first component A or the second component B it has with this color map. So another alternative, in that case, we can only, in the previous case, we could only analyze two components, but with this graphical solution, we can analyze 2 or 3 components, and we are going to use this function, which is the graphical component analysis, which here we have an animation that shows how this works. So this analysis generates a moving cursor that goes through component B to A, and then computes the number of phasors that lie within that cursor. So here we generate a profile of counts of phasor points along along two components, B and A, and then we do this for the combination of all the 3 components. So this is done by this graphical component analysis function that also receives as input the real and imaginary components, and then the real and imaginary coordinates of the components we want to analyze. And to do this, here we are going to simply plot these 3 components. Now we have 0.42, 0.67, and 5 nanoseconds. And the idea here is we specify this triangle of the 3 components, and we are going to analyze now the fractions from A to B, B2C, and C2A. So this is done by this graphical components analysis function in the components module. And then here we generate, if we want to specify the number of fractions we want to analyze, if we want 1,000 fractions, here we can specify it. If not, it's not needed. But here we are going to get the counts for each of these combination of components. Using this graphical component analysis, we give the real, the imaginary components after all the processing of filtering and thresholding. And then we specify here the number of fractions we want, the detail we want along those lines. In this case, we want 100 fractions between two components. And then we can see here, we can plot this using matplotlib simply to plot the three profiles of the combination of the three components. So here we see along the three combinations, no, from A to B, A to C, and B to C. Here we can see how the phasor points, the phasor clouds, are distributed along this combination of components. So that is regarding the component analysis. Now I'm very briefly going to comment on the thread analysis capability of the PhasorPy library, which we have this in the phasor module. Also, we have two functions that can be used to return phasor coordinates of the thread donor channel and the acceptor. And this can also be used to simulate different data we want. So here I'm just going to plot this using this other class from the plot module, which is phasor plot thread, which is here. It's similar to the phasor plot, but specific for thread analysis. And here we are going to see that we have all the trajectories of the donor and acceptor, and we can specify all these parameters from for thread analysis, the background, the donor for the acceptor, the bleed through, the thread efficiency, and the idea is that the ones that open this notebook, you can modify all these parameters and see what changes in this thread plot. And this can be very useful for this thread analysis. So I am not now going to go through hyperspectral image analysis with PhasorPy, which is also another advantage of PhasorPy that works also with FLIM and also with hyperspectral. Indeed, many of the functions you will see that are the same because once we read the signals and transform to the phasor space, in the phasor space, the functions used for modification and analysis are very much the same. So this is just some introduction on the theoretical aspect of how the hyperspectral information is transformed to the phasor plot. And I will not go too much into detail into that, just to show that in this case, the phasor plot for the spectral analysis now, instead of being just a semicircle from 0 to 1 in the G coordinates and 0 to 0.5 in the S coordinates, now goes a full circle between -1 and 1, both in the G and S. So now we have a full circle, and we are going to see how to plot this differently. So as I said, we are going to use now the read LSM function from the IO module that I went through at the beginning to show you that one example of these files that we can read with this PhasorPy library. So we are going to use an image of a paramecium that is also available in the PhasorPy dataset. module, and here we are going to read the signal, and in this case, the signal, as we are going to see, is located in the first axis. We need to specify that all the channels are located in the first axis. So here we see it's a 512 by 512 image with 30 channels. We see the mean average image, the same as before, and the mean signal along the 30 channels. And now we can use the same functions as before. So you will see that the general pipeline is more of the same. And we will use the phasor from signal function, which was the same function used for FLIM analysis. And the threshold and filter function also from the phasor module. In this case, the hyperspectral images don't need calibration as in FLIM analysis, so we're not going to use it, but the other workflow we are going to keep more or less the same. So we apply one time the median filter with a kernel size of 3 by 3, and with threshold the main with the mean intensity image with values less than 1. So we run this, and then we are going to plot now these phasor coordinates in the phasor plot. We are going to use the same phasor plot class as before, but now we have to specify all quadrants to true in order to specify now to show the full circle instead of the semicircle. So with this, we will see that this is plotted in the full universal circle. And we are going also to plot this 2D histogram the same as before. We can now change if we want some, we can also, I forgot to change this to contour if you want to also visualize this. Well, if we have time, we can see that later. So now we can also use the same as before, the cursors the same as before, because we are now in the phasor space, and we can use the same functions. So now I will show you different shapes of the cursors that can be used at the moment. So we have a cursor for circular shape or elliptic shape. And also we have polar cursors in case we want to mask regions of interest based on phase and modulation. So this is all in the cursors documentation. We use the circular, so I'm going to go through a little bit fast. This is the same as before. We use the mask from circular cursors function over the real and imaginary components already thresholded. So as you see, we select these two regions of interest, and now we see that the mask generated is of this shape is a 512 by 512 image with two masks that are located in the first axis. So these two masks are each of these two cursors. So then we are going to use the pseudo-color function to generate this pseudo-color image. In this case, I will not be using I will not be blending with the mean intensity image to show you that it can also be possible just to show these masks generated from these cursors. So the other shape we can use of cursors is the elliptic cursor. So it's very similar, but now we can specify a major and minor radius for each of the cursors, which is here. And so this will give us these cursors of elliptoidal shape instead of the circular. So this, what we can also specify the angle we want this ellipsoid in. If this is not specified, it will use the closest tangent to the universal circle. So in this case, we didn't specify any angle for this ellipsis, so it just went through the tangent of the circle. So here we selected these two elliptic cursors, and we are going to plot the pseudocolor the same as before. Here we are going to blend with the mean intensity image as before, just to check that we can do this also. Here we see. And then we can also specify the phase and modulation ranges in case we want to mask the phasor coordinates based on the polar space. So we are going to use the mask from polar cursor function, which this accepts the real and imaginary components. So we are in the phasor space. And then we can specify the phase min and maximum, the same with the modulation, to select these regions of interest. So here we specify the ranges for the phase and the modulation, and we call the function with these ranges over the real and imaginary components. So here we just plot how these cursors look in the phasor plot. Yes, here we see we use these two ranges of phases and these two ranges of modulation, and we can generate the same pseudocolor image for these polar cursors, the same as before. Great. So this is the end of the tutorial. I wanted to finish with going back to the official page of PhasorPy, where you can see all the documentation that we were reviewing along this tutorial. So in the API reference, we have all these different modules with all the functions and all the detailed description of each of these functions. I encourage you to go through each of them because we have a wide variety of tools that can be useful for phasor analysis. I just show you the main functions because of time constraint, but this we have a lot of tools available already to be used, and we plan to include a lot more in the short and medium term. Also, in the tutorial section of this webpage, here we have a lot of detailed tutorials of how to use PhasorPy and how to use the different functions. So, for example, this is the introduction tutorial where you can, here we show how to install PhasorPy, how to import, and how to read signals, calculate the phasor. You will see that in this case, it's very similar to the tutorial we already visualized, but we have more specific tutorials specific for each of the modules and all the functions. So, for example, here of generating plots from lifetimes, we have a lot of options, and the cursor analysis, the fret analysis also has a lot of detailed tutorials. So I encourage you also to go through these tutorials in case you are interested in some of these applications. And finally, I want to go to the GitHub of PhasorPy, which is the place where we have this library and where we work. And this is open for everyone that wants to contribute to this library. The idea of PhasorPy is to generate a community of bioimage analysis people and programmers. And it's open for everyone to contribute and include what they think that can be useful for phasor analysis in this library. So we have also in the webpage, we have a contributing guide here. So here we have very detailed also a guide how to contribute code, what are the requirements, how to create a pull request, and etc. And finally, if you find some errors or want to discuss something about Phasor or want us to include something in the library, here you can open an issue in the GitHub page of FhasorPy, and we will discuss with you. And also, if you have issues, problems, and new implementations, here it's also welcome to discuss about this. So this is what I wanted to show you in this workshop. I think I don't have any questions in the Q&A section. And I think that you can unmute yourself if you want to ask a question. If not, let me know, Chris, and I will grant you access. Thanks for everyone that's commenting in the chat. We are open for any issues you have. You contacting us, and we will help you with this library.